welcome to another episode of the Data Science Decoded podcast. It's been a little bit of time since our last recording due to various reasons, but we are back on track and we are showing up, so that's the important thing. Hi, Mike. Hi, Nir. How are you guys?
I'm okay. I'm missed our episodes. We have some technical issues with our with the Riverside, our tool with which we record our episodes.
Mm-hmm.
So, but now it seems that the situation is okay. We can record, and I hope from the next week we'll start recording regularly. And I'm really happy to see you guys, and I missed you.
Same.
Yes, same here. Everything's good.
Perfect. So to our listeners, today we're gonna break the record of the oldest paper we're reviewing, and you can see, or if you cannot see, I'll read it to you. It's in French, and it says general method for solving equations simultaneously. Maybe it's in French.
A system of simultaneous equations, yeah.
Yes.
Okay, yeah.
Or system
Thank
of
you.
equations.
Yeah.
And it's by Augustin Cauchy. So we're all familiar with him. He is considered one of the most prominent mathematicians in history.
Yep.
So I'll start by giving some background about him because he's an interesting fellow. He lived from 1789 to 1857. So this paper is from 1847, so it's a decade prior to his death. And he was French, and he did many contributions from calculus to even physics.
Mm-hmm.
And many of his contributions are rigorous proofs that they didn't exist prior. So if I'll give you a few of his, let's say, most important contribution. So let's say the Taylor expansion. He was the first that proved it rigorously. He developed in physics the Cauchy stress tensor. So people in material science are familiar with him. The Cauchy-Schwarz equality, right? Nir, you're a big fan. So
Yes.
there's many. There's like a long list.
Yeah.
By the way, Daniel,
Riemann equations, Cauchy sequences. Yeah, sorry.
No, it's okay. It's okay. I was trying to interrupt you. So, regarding the Taylor series, I was pretty sure that Taylor was the guy who invented and proved it. But now you just surprised me a bit that it was not the history wasn't this way, which I thought. So how it was? Who was Taylor? Do you know who is Taylor?
So that's a great question. We can check. So it says like in the history that Taylor's theorem existed before Cauchy, but Cauchy was the first to provide a rigorous proof. Okay, for it. Also really interesting to our engineers and mathematicians. So when you learn limits, the definition that are taught today is using delta epsilon, right? He introduced the delta epsilon definition of limits.
Interesting.
Yeah, so it's like everywhere. He's everywhere.
Yeah.
And like complex numbers, you have the Cauchy integral theorem. So like every course you do in undergrad, like Cauchy is there and did crazy contributions.
Yeah.
100%. So he was prolific writer. There's around moreover of 800 research papers published.
800?
800. Exactly.
Okay.
Yeah, and 27 volumes, meaning books. he published. Yeah, I don't know how it's possible.
I'd like to emphasize that he did it without using any language model.
Yeah. Yeah.
Or even a computer.
Yeah.
Yeah,
Just with the
or even
brain.
a printing machine. He
Yeah.
just wrote it by himself.
Yeah. Yeah.
And also interesting, his teachers when he was studying. So he was studying at the École Polytechnique, engineering, by the way. And his teachers, like advisors, were Laplace and Lagrange.
Hmm.
Okay,
So
I guess
again,
I guess he was able to generalize some of these results. Maybe some results of Laplace and Lagrange were generalized by Cauchy.
Yeah.
and so that's things that we all know. Some things we don't know that are really interesting. He was Catholic and royalist, so he was in favor of the monarchy, and also was pushing for Christianity.
Hmm.
So after the revolution, French Revolution of 1830, he refused to swear allegiance to the to the revolution. So they sent him into exile.
Hmm.
So that's like interesting. Another things is that he had a really difficult personality. So many mathematicians had problems working with him. And also he turned down a royal honor. So from Sweden, the king back then wanted to give it to him, and he said, no, I won't accept it because the king of Sweden wasn't Catholic. Okay.
Okay,
So again, really like
fair
interesting.
enough.
Yeah. So anyways, that's about Cauchy, and I'll just add that prior to this episode, the oldest paper was Fisher's paper from 1921 about estimation and maximum likelihood. So we broke the record and we went back 80 years around prior, and now with Cauchy. So we'll start. It's a short paper. It's translated from French. I couldn't find the original, by the way, and I looked quite a lot, but we're with the English one. So I'll read it to you. It states, being given a system of simultaneous equations that the concern is to resolve, one begins ordinarily by reducing them to a single one by aid of successive eliminations. Save to resolve definitely if it is able the resulting equation. Well, I'm not sure I understood this, except that you're trying to reduce them to one single equation. And then he has two observations. But it is important to observe, one, that in a great number of cases, the elimination is not able to be affected in any manner. And two, that the resulting equation is generally very complicated, even though the given equations are rather simple. Okay, so before I continue, can you give some motivation? Maybe Neil, what he's trying to do here?
I think what he's trying to do is formulate this optimization problem kind of like Newton, in which you want to take a.
What's the problem he's trying to solve before
The
the
problem is,
solution?
let's
Like,
take a cost function to zero. That's the problem. So u is f of xyz, and it can be more variables, as we can see. Is the function of xyz and more variables, and we want u to be zero. We want to find the values for xyz for u to be zero, and that is what we do in, I guess, when we have a loss function and we try to minimize it. So basically,
okay, so that's already the solution.
Yeah.
I'm more focused on the problem, and as far as I understood, and correct me if I'm wrong, he's saying where you deal with multiple equation with multiple variables. Okay, so let's say I think he was working on like astronomy, right? Trying to model how planets
yep, yep,
evolve whatever, and then you have different equations of motions. So he says the usual approach is to eliminate variables progressively and then to reduce it to one equation. And then there's two problems. One, elimination is not possible, or the resulting equation is becoming very complex.
Yes.
Okay, so then he says,
Daniel, very small comment.
mhm,
By the way, the assumptions stated in these 2 or 3 sentences don't hold for the linear systems of equations. For linear systems of equations, we can quite easily reduce them to one equation. We can do it
mhm,
by many methods. You know, you can
mhm,
just turn your matrix and with which you define with which system of linear equations is defined into upper triangular with some Gauss method. You can easily solve, but in case that some of the equations are not linear, you just in many cases you just can't do it. For example, imagine that your equations say for the planets, and I think it contains some sines and cosines and exponents, and you just can't express one variable explicitly as a function of the other variable. So what you can do, you can solve it numerically, or you can do something more clever.
mhm. Yeah, so I think that's what he's trying to imply here. He says for these two motives, meaning it like the one equation maybe is too complex, one imagines that it would be very useful to understand a general method which may be able to serve to resolve directly a system of simultaneous equation. So now he's trying to talk about his idea. Such is that which I have obtained, and of which I'm going to say some words here. I will limit myself for the moment to indicate the principles on which it is founded, proposing to myself to return with more details on the same subject in a forthcoming memoir.
Okay.
Cool.
I have a comment here. So
Yeah.
I read about this, that this forthcoming memoir was never found.
Ah,
So
interesting.
Cauchy has laid out the method here without any proofs or convergence analysis, and that's it. That's where he left it.
Interesting. Why he didn't do it? Because he was super rigorous, at least in other
Yes,
domains.
yes. That's why it caught attention. So they tried to
Mm-hmm.
find this memoir, didn't find it. Maybe it existed and he didn't publish it. Maybe it didn't exist.
Yeah.
I don't know. Maybe it
Thank you
didn't
for
exist.
that.
He
Yeah.
couldn't write
Uh,
some. He couldn't write a comment similar to those of Fermat, but he doesn't have enough place
uh,
to publish this
Thor-
memoir.
yeah. So he defines u, which is equals to f, a function of x, y, z, but could be many variables. And he says which never become negative and which remains continuous, at least between certain limits. And then he says, okay, in order to find those values of x, y, z, which will verify the equation, u equals to 0. Right, so again, we're trying to find some function in high dimensional space when it's equals to 0. He says it will suffice to make decrease indefinitely the function u until it vanishes. So again, he talks about like some kind of minimization. And then he says, now let those variables x, y, z be particular variables attributed to variables x, y, z. So now they're like specific realizations.
Mm-hmm.
And then he describes capital X, Y, Z, which are values corresponding to dx of u, dy of u, and dz of u. I view it as a derivative, right?
Yeah, partial derivative. Yeah.
Yeah. It's the partial derivative. And alpha, beta, gamma, some very small increments attributed to a particular value.
Mm-hmm.
So now he's like doing a small step, right? He's saying the new x is x plus alpha, and the new y is y plus beta, and z is z plus gamma.
Mhm. Yep.
So that's like small increments. And then he says, okay, now this small increment around those values, it's like Taylor expansion.
The
So our
first order.
mu first order, yeah.
Yeah.
First order Taylor expansion. Exactly. Thank you for that.
Mhm.
So we have the function at that point plus the small increments around it. That's why they use alpha x plus beta y plus gamma z,
Yeah.
which are their derivatives.
Yep. Yep.
And I think you mentioned it, Nir. This derivation is similar to Newton's method. Makes sense?
Not quite.
Or it's not there? Not there
No,
yet?
not quite.
Or
No. We're not there yet. No, this is not Newton's method yet. No.
okay, so tell me where it is.
Okay.
Then he says, we imagine now that theta being a positive quantity, one takes alpha to be minus theta x. Again, x are the derivative. Beta to be equal minus theta y, a capital, and gamma to be minus theta z, capital.
And then this theta is known as a learning rate in machine learning and deep learning.
Yeah, or step size in gradient descent. We call it in machine learning. You call it learning rate, yeah. But in optimization, we call it step size. And capital X, Y, Z are the partial derivatives again with respect to X, Y, Z.
Yeah, and this is eventually proportional to the negative gradient, right?
Mm-hmm. Yep.
And yeah, as you said, theta is the step size.
Mm-hmm.
And now when he's substituting those definition into the function, this function is always decreasing because this value here, which is theta times open brackets x squared plus y squared plus z squared, again the derivatives, is always positive.
Mm-hmm.
Yes.
Yep.
And now it's easy to, it says it, I like, it's easy to conclude from it that the value of I think it's capital theta of
theta,
of u determined by the formula theta equals a function of this small step on each dimension. So it's x minus theta capital X, y minus theta capital Y, and z minus theta capital Z. So just doing again the small steps around it. And because this capital theta is always smaller than mu, that means that each step decreases the function's value.
Mm-hmm.
Because you always are subtracting a positive value. And then
yeah,
he says,
but still, I'd like to emphasize that you are subtracting this small value from the first order Taylor approximation of this function. It is not this function, but the first order Taylor approximation. It is very important. It is not exact equation, but an approximation.
okay, thank you for that. It's important point. And now continue. Will become okay. He says, yeah, this equation will become inferior to u, meaning lower, if theta is something extremely small. And he says, if now theta comes to increase, and if, as we suppose, the function f of xyz is continuous, the value of capital theta of mu will decrease until it vanishes, or at least until it coincides with a minimum value determined by the equation in a single unknown. D of capital theta equals 0. So it says it might come to like a local minima.
Mm-hmm. Yeah.
By the way, now former mathematician is speaking inside me.
Mm-hmm.
He's talking here about function, about continuous. How can I say the functions about the function is continuous, and he's talking about it several times. But as far as he assumes a first order Taylor approximation, the function is differential, and any differential function continues. And he keeps talking about this continuosity. I don't know how to define it in English, and it is a bit strange because you are using first order Taylor approximation, so you assume the function is differentiable, and
Once at least.
yeah, and it implies that it is continuous, and he keeps mentioning it that it is a bit strange. Maybe it's some problematic translation.
Yeah.
I
And maybe again, it was written almost 200 years ago. Many concepts we have today, it didn't have.
Yep.
okay.
So
That's true.
Okay.
But
Fair enough.
this paper is mathematicians raise their eyebrows on this paper because this is the less rigorous paper of Cauchy, at least from what I read in history.
Okay.
So I just want to add here before we continue. So in a sense, he described here to listeners an algorithm which is similar to gradient descent in order to solve this cost minimization or minimization problem.
Yep.
And we had already reviewed the paper that we said maybe it's one of the first gradient descent algorithms, but this could be one of the first papers to discuss it, right?
Yeah.
Nir, what do you think?
Oh, 100%. Yeah. Yeah, I actually referenced this paper in my master's thesis, and also I was maybe 10 years ago when maybe more even when Andrew Ng machine learning course went online in YouTube. He presented the gradient descent to the class, and then he said, "Congratulations, class! You just learned your first machine learning algorithm." And I refuted that by saying that this algorithm was invented in 1847, hence it's not a machine learning algorithm. And he never replied. Yeah.
Many stuff in machine learning is just about optimizing function.
Yeah.
What we're actually doing in machine learning, we are trying to minimize our loss. And what is loss minimization? Just optimization. So
Yes.
gradient descent, for me, I defined it as an optimization technique.
Yes.
And machine learning is just optimization is at this core of machine learning. So you can call it machine learning technique as it is heavily used in machine learning, but still, the historic reference proves us that it is an optimization technique. And
yes, it is.
Long before machine learning.
Yes, a lot longer, like 200 years before. Yeah.
Yes.
And here it's an important part. He says now, let's say we solve the system of not system one equation mu equals to 0 using this gradient descent. But now what happens? We have a few different equations. So he says, okay, cool. There's mu equals 0, v equals 0, and w equals 0, etc. So what we can do is define a new function which takes each one squared and adds them. So you have u squared plus v squared plus w squared, etc. Equals to 0. So you create a new equation, which is, because it's squared, it's the only way it will be 0 is that each one of those equations is 0.
It is fully
so
equivalent.
then you can so you can still apply the minimization on this new equation, and if it works, it means you also minimized each function. Which again is it's not rigorous, it gives motivation.
But we do that in machine learning, right?
Yes.
Yep.
And here he says,
yep. Now, if
one wishes to obtain new very rapid approximations by the aid of the linear or Newtonian method, of which I've made mention in the memoir of 20th of September.
Yep. Now, the linear method, I think he's referring to least squares. And Newtonian method, it's referring to Newton's method, Newton-Raphson method. By the way, Newton's method was already in existence from 1669. reformulated by Raphson in 1680, I think.
Okay.
And Gauss's method of least squares was in 1804, I think, like maybe 40 years before that, which was then disputed by Legendre, and they had some sort of a argument about who discovered this earlier, and Gauss was completely. I think that also Gauss was not a very friendly person. I don't know, just from what I read. And he said, I did not imagine that Mr. Legendre could feel so strongly about a simple idea.
You know, then you look at it now, after we learned math for many years. It is it is a very simple technique, but 250 years ago, it was not. I don't think it was very simple.
No.
Now it is, but
Yeah,
but
maybe
then,
for Gauss, yeah.
yeah, maybe for Gauss.
Yeah.
Do you know this famous story about Gauss? When he was a kid, and the teacher
Yes.
in his school asked them to add all numbers from 1 to 100.
Yes.
And then after 1 minute, he told them he solved it. And he solved it in a very clever way. He just regrouped them, 1 plus 99 and 2 plus 98,
Yeah.
So maybe for Gauss it was simple even 250 years ago.
Yes, that I have a book about Gauss, and I read this to my kids. This story about Gauss. He basically invented the arithmetic, the sum of arithmetic series formula when he was in first grade. So,
that's exactly what Mike said. Yeah, that's the same.
Yeah. That's what Mike said. Yeah, yeah, and yeah. So it was simple for Gauss.
Yes.
Yeah.
And I'll just finish. So the paper is finished by him talking about how this method is advantageous for determining the orbit of a star, right? So again, he was probably trying to solve those equations of motion, and then he said, okay, I'll develop some method to do it. So that's the paper, or at least the translation. It is quite short, and it's extremely not rigorous, at least for his standards. But it is probably the first, or one of the first papers, as we said, that talk about like gradient descent.
But
we use it often.
But due to this low rigorosity of this paper, it is a perfect fit for a podcast. You can listen to it. You don't have to have these formulas near your eyes. You don't need to look at the formulas. It is just, you can just listen and then understand. The math is very simple and not very rigorous, as you mentioned.
Yeah, so you're saying, Mike, you want the next paper to be philosophical. I see where you're going. You don't want math.
I'm not sure about philosophical. I'm not strong at these philosophical issues, but we can try. I can use some LLM to understand this philosophical paper, because it's quite more tough for me than math. But yeah, let's go. I think we did some philosophical paper.
We did. We did Turing test.
Yes. No, Turing test is not very philosophical. Minsky paper, right?
Minsky was a review, actually.
Okay.
He reviewed regular papers. The philosophical was the Turing test, because there was just thought experiments there. There was no math.
Okay.
Yeah. And maybe we can do like an influential paper. We should think about it in the philosophy of math, meaning, is mathematics exist unrelated to us, right? Or we invent it as a language to describe reality.
Yeah.
And there's more views, right? So there's like a few different views in what is math. So that could be an interesting episode.
Yeah. We can try to address the famous saying that the math is a queen of all sciences, and we can discuss I personally agree with that because I really love math, but I think there may be others that who
Yeah,
disagree.
I would dispute it
Okay,
because
okay,
math is not science.
okay.
You
know,
there is a scientific method, and it's extremely not meaning. Okay, I don't want to derail it, but something which is rigorous like math, it's not scientific.
Back to the paper for a second. It's interesting to see that I think a lot of these old mathematicians have developed this technique and other techniques in order to solve real life problems. Kind of unlike pure math of nowadays, which sometimes it's completely not related to real life problems. They observed some natural phenomena, for example, stars or planets, and tried to solve this, to derive systems or derive algorithm to solve what they wanted to solve. So it's kind of like more engineering, less math, in my mind.
Yeah, I think the motivation was more
Yeah.
applied.
Yeah, yeah.
And then it changed.
Yes. I think now. I think at the moment most of the easy and very easy problems, very easy real problems are solved, and the rest are very complicated, and then the very complicated problems. And the people and mathematicians of today's mathematicians are struggling to solve these complicated and very complicated problems, and I think it is the reason that they're trying to invent some kind of imaginary problems which they're capable of solving. And this is my explanation, but it also can be easily disputed.
Yeah.
Perfect. So that was a really fun paper, and the oldest one we did. Maybe we'll break the record in following episodes. As Nir alluded, there's a few even older concepts that are relevant to what we do today as data scientists, as also mathematicians, statisticians, etc. So we might review them in future episodes. And that's it on my side. I would wish everyone a great week. Also, you,
too, guys.
Mike, Nir, and the listeners. And I'll see you next time.
See you next time.
Until
Bye-bye.
then.
Yeah.
Bye.